So good morning. Today we'll be going uh, talking about repeated field number, and for this particular course, for this particular part, I referred. Sorry, I referred this by Bhavikati, a limit state design to AS 800 2007. This is the textbook which I kind of opened and saw, which probably is to adapt your current code verbatim. Okay. I'm using some other textbooks also, but I'm not going to mention that right now. For today's lecture, this is more than sufficient. Okay, along with this, we'll have to go through your IS 800 also, IS 800 2007 for understanding the various provisions. Okay. Now I'm again going to go through the what I call as the common shapes, which we have already discussed earlier. Okay. So basically, if you see, the rod shape will probably be the most efficient section for taking up the tension. Okay. So you can see these are some of the forms in which the rod is provided, and again you can what one of the advantages you have with the rod is you can tension it a little, pre-tension it a little, so that it will not go into the compression zone too easily. So it can have a lot of beneficial effect. Now this is another form of the circular, but this is a circular section. This is a rod, but this will not be solid. This will not be solid. Now when you're increasing the diameter, essentially what happens to the material, the stiffness increases. Okay. Now, probably you'll wonder why is there the requirement of stiffness for a tension? Typically, tension members don't occur. I'll just go to thing like no. These were the sections we saw. I'm sorry, I'm jumping back a little because I feel that it'll be instructive to have a look at this section. See, we were talking about tension compression elements. That is, these elements many times will be taking tension and then also compression subsequently, except for the case of cable structures, except for the case of cable. For example, if suppose you are going to have a telecommunication tower, okay, that could be a guide tower. So these are guide ropes which are placed so that this element will stay in position. So these guide ropes will always be only in tension. So suppose wind is acting in this direction, these two will be in tension, and this member will be in. It will not have any force. This member will not have any force, and this pole will always be in compression. Right? But if you are looking at the typical picture which I am showing here, this will alternate between tension and compression. Okay. So these are some of the other combinations we saw. Okay, we also saw that voltage functions where they don't take moment and then they have moment. I should have this recapitulation. But if you come now, you just have a look at this element. You'll find that here you are having a rod which is having significant diameter. This significant diameter enables it to take compression also safely. Okay. The stiffness will prevent it from buckling. Stiffness which is got prevents it from buckling. Now, I do have a question for all of you. So probably we can I'm just opening a quiz right here. So those of you who are not having the questions can have a look at it. Probably make the answer, go out, and then attempt. You can write in a piece of paper also. Those of you who are not having the internet inside that, make a note of the answer. I'll make it around 9 to so that when you go out, you can see the answer. You just be honest to yourself. So now here if you see the question is which is the connection which is unable to carry moment. So you've got three connections. Which of them, which of the connection per se carries moment. So you can answer your question. These are the answers. So I'm not able to show both of them. So this is the thing. Probably you can see which are the connections which can take moment now for a minute. Then I'll change to the quiz. Sorry? Start. This is having quite a long time. This is having at least 9, 10. By the way, I set it. You can start attending the quiz. If you are attending the quiz directly on Moodle, you don't have double. You just do it one shot. Okay. So if you are able to right, so I'll go on to the next part. See, the first section we talked about is rods or cylindrical shaped elements. Second is plate. Okay. Now you see here, this is a gusset plate. This is a gusset plate. This gusset plate can be in tension or compression, but I am looking at it only when in the case where it is under tension for this class. Okay, I'm just looking at the plate in tension in this class. So you see there are three types. See here there is an angle connected with one leg with 4 bolts. Okay, then you got two joists, okay, connected by a plate, and it's also pinned. Okay. So this is just look at this three diagrams A, B, and C. I think there is a question based on this also. So there is this is nothing a sheet of metal which is taking up the tension. So what happens normally is when you're designing for tension, you find that steel is very good in tension. So even a very small thickness will be able to satisfy the requirement from pure tension consideration. However, design engineers, we have to also think of one more aspect, which is the weather. Okay, when it is exposed to adverse conditions, steel tends to rust. So you should have what we call as a corrosion allowance. And the corrosion allowance will usually be increased when the steel member is inaccessible for inspection or maintenance. What is the maintenance required for steel structures? What is the maintenance required for steel structures here? Sorry, regular painting. So that is basically what the only thing which you need. Suppose if it is a pin connection which requires greasing or oiling, you have to do the greasing and oiling, and ensure that all the bolts are having the required is having the required tightness. Okay. So now, please, there is a choice. Okay, here there are three questions: bolts in single shear, which is the bolt in double shear. Have a look at this diagram. Which of the bolt is in double shear? And just have a look at it and give your answer. Then which are the gusseted connections? That is the second part. And the third question is which is the bolt double shear? So the answer, I'll just give half a minute to answer that question. Sorry, I'll probably keep it like this. So which is the bolt in single shear? Which is the gusset plate? And which is the bolt in double shear? Okay. So these are the angle sections. These are the various forms of the angle section. Okay, so you can arrange the angle in any of these patterns. Okay, back to back, and then this is actually this is channel. I don't know why I put it here. This is channel back to back, but this is angles which are again kept in with the legs together, and here the legs are apart from each other. In fact, this is the pattern which you see in the railway stations a lot. Yeah. Yes. Sorry. Okay. Now there can be wire or rope also. Okay, as the tension member, you can always do that. The cable, what I'm showing here is a cable which is essentially multi-strand. Have a look at this. I'm sure you will be able to identify this structure. If you look at it, this is one of the structures where the optimization is maximum. Most optimization is done for this structure because of the number of repetitions these structures undergo. These structures undergo a lot of repetition. So if you save even a few kgs of steel, it becomes quite significant in the long run. Second thing is, most of these structures are in inaccessible places. So if you're going to have a very huge section, the cost to carry that section is going to become very high. And then have you seen these towers being assembled? How many of you have seen these towers being assembled? You'll find that the person climbs up, he'll let down a rope, pull up each element up. So it should be so heavy that a person can lift it. It should be so light probably. It should be so light that a person, single person can handle each of these elements. Okay, and these towers are very tall. These towers are very tall. Now the design consideration is uh, whenever you are having a compression member, the unsupported length is very large. At that time, it will buckle. So you will see that there is a pattern which they try to enforce to ensure that the tower is doesn't have very long unsupported. So if you'll see that there are many elements which break subsequent elements length. The length of all the subsequent elements are lesser. Again, you'll find that there is a bracing. This, if you see, there is an X pattern goes to bottom to top. Sometimes you'll find that there is an X till one level, and then we got what is K bracing. So which will look like an inverted K. I think it's also chevron bracing. But in any case, this is a place where you will find that angles are only used. It will be very light for each element which is there is very light for the tower which is the final product. Okay. So in this part we saw the various sections which are being used. Now those of you who are having IS 800, I'll request you to please open up your code book. I'll request you to open up the code book and see refer section 6.1. Okay. Now in section 6.1 you'll see that this is the clause which is there. I am summarizing this clause right here. So first they define what tension members are. They take up loads which tend to stretch them. Okay, and then the benefit of tension members is they can sustain loads up to the ultimate load. This is nothing but what we have done in the tensile test in the strength of materials lab. Okay, now ultimate load, the difference between tension is that it go up to ultimate load, but then compression member still also in buckling. So that is something which we'll have to have a look at. Okay. Now, this is a limit state. This is a limiting state for the tension members. Second, there is another limit state where the structure could fail because of excessive yielding. It might have yielded to that level that the usefulness of the structure is gone. The structure is still safe, but it has undergone excessive yielding. Okay, so now there is a question. Look, there are two limit states. One is in green, one is in red. You have to use one word to identify which is the red color limit state. Okay, and the next question is what is the limit state which is marked by green? Only one word should be used. This is done also in your uh, concrete design. Okay, in limit state of concrete, LSD of concrete also you have got this. So just find out what is that one word which is used to define this green color limit state and one word which defines the red color limit state. So just identify those two. So what is the green color limit state? Limit state of, you can have a look at your IS 800 for this. Okay, look at your IS 800. Choose which would be the appropriate limit state, what is marked in green, and what is the appropriate limit state for what is marked in red. Okay. Now, tension members need not fail only due to tension. If the connection fails, then also it is as good as failing. If, for example, in a tug of war, if suppose the rope breaks, the rope has a failure. Suppose the people it at one end leave it, then also what happens? The rope is not able to take tension. So these two, this block shear uh, is one kind of failure, and then I'm putting tension failure of connection. Actually, it should not call it as tension failure of connection. Tension failure at connection. I'm going to just rephrase it a little. Tension failure at connection. Okay, because at the connection you usually have, if it's a welded, the weld can fail by tearing. The section is least when there's a bolt hole, so the section can fail due to tearing at that point. So actually, you see in the bill books, there are a lot of holes. When the person tears, where does the bill tear? Come on here, you would have seen this, right? In a medical shop, you see that they got a holes mark, perforations made. When they're tearing it, where does the paper tear? Sorry? Okay, look. Suppose I'm going to simply pull on this page. Okay, I'm simply pulling on this page. Where will the paper tear? Along the dotted lines, right? So this is, why is it so? Because the cross section is least at that point. Okay, so please remember this is a very common, like, concept which you can easily remember. So that is why remember the last bit of the cross section. This is where it all comes into this. So the first is block shear failure. Now please have a look at this connection over here. If you see here, initially the entire thing would have been inside. Okay, it would have, the entire plate had been here. Now the entire part of which I am marking in red has just come out. It's just come out as a block. Okay, such a failure is called block shear failure. This again happens when the connection is tension. Okay, so this is the gusset plate. Okay, just this is the gusset plate, and these are the bolt holes. Okay, and the entire part has come out. So this is called a block shear failure. Okay, this is called a block shear failure. If suppose you are going to look at it from finite element analysis, this is how it would probably look like. So you can see the stress concentration in the places where it is in. What is the point? Please, do you have anything to share? Please, if you have anything to share it. I really mean it. So usually this kind of a girder is, this kind of an arrangement is seen in the uh, bridge, okay, in the bridge girders. Now this is an example of tension failure. Okay, this is an example of tension failure. Okay, I got a question now. This is very general question. So failure mode of tension member is, so there are about quite a few choices over here. So I need you to when you get to the answer, you can directly answer this. You don't need to It doesn't have any of the other questions which is there. Okay, only 5 questions. So when you go out, please answer these 5 questions. Okay, whenever you so now if you see here, this is a place where you can very clearly see that it's a failure intention. The bolt, the bolt hole. 1 minute. Let me just take another pen. Yeah. So if you look at this area, you'll find that the bolt has reduced the bolt hole has reduced the area of cross section so much that when this paper was when tension was applied on this paper, it has failed. Okay. So again, this is a place where the bolt has failed in tension. I'm just illustrating tension failure in this. So if you see here, you'll find that the section cross section was reduced in this portion because of the thread. So when the bolt had been subjected to tension, it has failed. The bolt was subject to tension, it has failed. Okay. Now, if you have a look at this member, this is after an earthquake that this photograph was taken. So if you look at it, in this region, the tension member has just got cut, and it is cut. So these are some of the common modes of failure which we have in tension members. So I think that's yes. And this is about yielding. So the member can yield. It means that can you see how the section has reduced here? The section has got reduced greatly in this portion. Okay. So these are ways the member yield. What is the failure of section? So you also see action, fail, fail. Also see fail. So essentially, you have this is the so now we are just going to the design criteria which has been given by IS 800 2000. Design criteria is given by IS 800. So here what happens is this is the basic equation which we have for this is a very common. I mean, this makes a lot of common sense. Whatever is the force that you are going to get, it should be much lesser than the whatever the force which you are going to apply. It should be much lesser than the force which the section can take. So this is the equation which we have here. And if you look at it, there is a point that says this is the lowest of design strength. So we are saying that this is the lowest of design strength. So there can be more than one design strength which we have. So what do we do in the tension design? We see the various modes in which the member can fail. We find out what are the various modes by which the section can fail, and based on that we will be proceeding. Now if you look at it, uh, the first mode of failure as we see in IS 800 is by the yielding of gross section. The yielding of gross section. What does yielding of gross section mean? The cross section which is having the least area has yielded fully, and then the member has failed. Failed because the stretch the elongation has been much more than what is the, because the elongation is much more than what is the, so this formula I have repeated here. So TD, that is the design strength due to cross section, the design strength due to cross section failing would be area of cross section into Fy, that is the yield strength, divided by gamma m naught, divided by gamma m naught. So now gamma m naught is from table 5. If you remember, this was discussed. So irrespective of the place where the bolt is fabricated, the is 1.2. So now I'm just going to go for a very simple example where we look at the yielding of the cross section. Okay, yielding of the cross section. So from that consideration, what would be the safe load? Okay, find the maximum tension that can be taken with a single bolt. I have to add one very important thing over here due to cross section failure. Okay, because there are other failures also. So in this case, we are only looking at due cross section failing. Okay, so again we'll look at the formula. The formula is TDG is equal to AG into Fy divided by gamma m naught. Okay, so if you look at, sorry, so gamma m naught. So what AG? What is the AG? Now I'm going to take IS angle 60-66. So how is this connected? This is IS angle 60-66. I'm going to say, okay, so I've been marking this 12th thing, and which is having a bolt here. There's only one bolt. What is the diameter of the bolt? Here I'm talking about M16 bolt. Okay. Now what is M16 bolt? M16 bolt is the Indian standard designation for 16 dia bolt. It is the standard 16 dia bolt. Okay, now if we have a look at this side, the view from this side would be something like this. This is the gusset plate. You are having the angle like this. Okay, so this is 60, 66. You need to open your steel tables, okay, and find out the area of cross section of 60, 66. Now, if you look at the angle, what is the area? And the bolt hole is somewhere here. The bolt hole is somewhere here. Which is the area which is under tension? Is it the is it both the legs, or is it only the flange in this case? So at this point, where, if I'm going to just see, the load is going to bear on this, right? The load is going to bear on this. So there is only on this bolt, the entire tension is being carried. Okay. Here, the bolt, the L shape is, shear lag. Okay, we will go into that shear lag a little later. So we will go into the shear lag a little later. But for now, let us just say that this is the only place which is under tension. What I am doing is I'm just going to take the area 66, that is 8.96 centimeter square, or this is 896 mm. Area is 896 mm square divided by 2 minus the bolt hole. Okay, because we want a gross section of area. We want a gross section of area. So this will be, I'm using M16 bolt. So the bolt hole will be 2 mm more than the bolt diameter. It's nothing but 18, and this angle is 6 mm thick. Okay, so this is the gross section of area. And what is the Young's modulus of steel? Sorry? Okay, 2.1. Okay, 2 into 10 power 5, that's also fine with me. Or 2.1 into 10 power 5. 2.1 into 10 power 5. And then you got gamma m naught. Gamma m naught is equal to 1.25. Okay, gamma m naught is equal to 1.25. So you substitute in the formula, get the answer. Okay, you got one more problem where it is only 90 by 6. Again, there is only one code. Please work this as a homework, and on Wednesday or Thursday, okay, on Republic Day, I'll open the link for submitting your answers. Okay, all the 3 homework problems which you have done till now, you will have to submit your answers on Republic Day. Okay. Sorry. So today we saw tension members. Do any of you have any doubt in what we have seen? The next concept which we'll be going through is shear lag, which we'll see in the next class. Okay, so this is just a introductory primer to structural design of tension members. So any doubts, please?